coming from a cold polymetric.
Thank you, Rachel. Thanks for the organizer for this invitation. So today I want to talk about the subject is the title. So I will talk about vanishing p-cohomology in group 2 for most semi-simple groups of rank this group. So first I should introduce what is the p-cohomology. Well, there are different notions of p-cohomology. So for instance, like the easiest to define is for a simple complex. So if you take a simple complex that has bounded geometry, you can take your classical simple cochains and you just look at those that are LP. And now, because of your bounded geometry condition, your classical simple differential will give you a bounded operator. So you will have a new cochain complex on which you can take the cohomology. But I will not be talking about this. I will be talking about groups. So I want a notion of group LP cohomology, and in particular it will be for locally compact groups. So the first thing I will discuss is continuous cohomology. So this is a rather general construction where you cook cohomology groups starting from, so you start with G, locally compact, second countable, and with rho D, continuous representation of G on a Banach space. Well, say on a Banach space, it could be a special Banach is enough. So when I mean continuous representation, I just mean that the map of D times C to V, well, you know, since G, rho G or V is continuous. Right. Okay, so when you want to define cohomology, you need two things. You need cochains and you need a differential. So your cochains here, some positive K, and you look at your group CK, which will be, I will denote it like this. So the cochains from G to V. So this will be maps from continuous maps from GK plus 1 to V, and that I will ask them to be equivalent. So, well, this condition corresponds to invariance in the space of continuous maps from GK plus 1 to V, and the natural G action that you can put in there, the invariant vectors give you equivalent maps. So these are maps from GK plus 1 to V that are continuous, such that C of GP0, GGK, so you just act diagonally on each of the coordinates, is the same thing as rho of G of C of G0, GK. For every G and G0, GK. Right, so these are your cochains for your cochain complex. And second thing you need is a differential. So you define differential CK from CK to CK1. And these are just, well, it's the classical simple differential. You just want to associate the alternate sum of, so, well, you want to evaluate something on K plus 2 elements. And the most natural thing to do is just to associate the alternate sum over the, where you just take out one of the elements. So it's the sum from 0 to K plus 1 of minus 1 to the I, or C is 0. And I know this for taking out the I element, then I go to the question. Okay. Well, so this is rather formal, it's just to give you a definition. So what I want to define now is just, I want to define the cohomology as the cohomology of this cochain complex. So K continuous cohomology of G values in the representation V if the kernel of the K quotient by the image of GK91. So this as a vector space, this is a topological vector space. But it is not much more than that, in the sense that this image may not be closed sometimes. So this space is maybe not Hausdorff. Well, and if you want a really whole surface, you just take the closure of the image here. This will give you what we call reduced cohomology. Right. So today, I will look at one particular representation. So today, I will take my representation V will be LP functions on the group. When I mean LP functions on the group, I mean with respect to the R measure. So it will be left R measure. And P is just a real number like this one. And my representation rho, so the action on LP functions will be rho translation. So notice there's a small game here that I'm playing. I chose the right translation and I took a left R measure. And this is not a coincidence. Later, so so the result, I mean the reason of why one does LP cohomology is main reason is that LP cohomology gives you quadrimetry invariance for every P and for every K. So this is a theorem. Well, okay, in the context of group cohomology, it's the Darwin hurdle. And the Bourdon, because there are slight differences in the setting. So they look only at L2 cohomology. In fact, they look at L2 Betty numbers, but the proof is more or less the same. But this term is older in other settings of LP cohomologies, notably for, say, for simplicial LP cohomologies was already known from Conçu much before. So the term is following. If so, let G1 and G2 be two locally compact second countable groups. Naturally, I want to put metrics on them. So any locally compact second countable group carries a left invariant proper metric with left invariant proper metrics. And the point is that if G1 is quadratic to G2, then for every P and for every K, the cohomology spaces are the same. So in HK of G1, the values LP in G1 is topologically isomorphic to the HK of G2 and values in the LP of G2. Okay, so just before I said that, I took a left R measure and the right translation. And this is important because if you take a non-unimodular group, your left regular representation, the right regular representation are not necessarily the same. And in particular, this will be false if you take left and left, or if you take it right and right. So you have to take, it has to be like mixed. And in particular, also, this is another remark maybe that I should make. Notice that the representation rho, so LP of G with the right translation, this is isometric. This representation is isometric even only if your group is unimodular. Yeah, well, G is the group in there. So this is just because, like, say you take F and LP function. Well, you want to compute the norm of rho G of F. Well, the norm of rho G of F. So you just act on the argument. This is in fact the modular function of G to a given power, so it will be -1 over P times the LP norm of F. So you see, like it's exactly that. This is isometric if and only this thing is bigger. It's equal to 1. Right. So this is just to tell you that, in fact, I would be interested in working with non-isometric representations, and this is important. I want to give an example to, well, I will not use it later, but it's just, I think it's important to give an example of how does one use this theorem. So this is an example you can consider that allows you to distinguish two groups that look really similar, but they turn out to be not quadratic. So we can look at the groups. Say the top is a grid plane, which is isometric. You can view it as R symmetric product with the Heisenberg group on 3 variables that appear in your talk. Where the factor R acts on Heisenberg by like the classical Carnot homoscedastic. So you act by exponential t on the horizontal variables, and you act by exponential 2t on the vertical variable. And the other group I want to take is R symmetric with R3. So the Heisenberg group on 3 variables is modeled as a manifold on R3, but the group law is different. And here the action that we put is the same as the Carnot homoscedastic. We put exponential t, exponential t, exponential 2t. So these two are two negatively curved groups, which look really similar, but they are not. In fact, they are not. And they are not isometric because one can compute the p-cohomology of these two groups in degree 2. And in degree 2, in fact, there are values of p for which the cohomology of this one is Hausdorff, and the cohomology of this one is non-Hausdorff. All right, so it's just to give a concrete example of what this theorem can
So the green in the K, right?
Yeah, for the grading K. I mean,
And you say that you can find, given the K equals 2, you can find P's.
Yes.
That's that they are different.
Yeah, and in particular, I think it's something I remember well to be K equal 2 and P. I think it's the P's between 2 and 4. I think between 2 and 4, there is a place where this cohomology turns out to be Hausdorff, while this one is not Hausdorff. Something like that. Right. So. Okay, it's a nice polyisometry invariant, but now there is a problem, right? We have an invariant, naturally we want to compute it. And the problem is that, well, computing it turns out to not be so easy. So, now I would like to present computations for semisimple groups. Well, though many of the techniques also work for other groups, as solvable groups. Now I want to talk about p-cohomology of semisimple groups. Right. So since we do not know too much, I begin with a question, which is the motivating question, and that in some sense directs the results that we know. It's a question from Ramos, 1993, and he asks the following thing. So let G be semisimple group over a local field. So when I mean a local field, it can be Archimedean or not. So if you want, as an example, I mean, you can take epsilon R, you want an Archimedean field, a group over or the reals, or you want, you can take epsilon of 50. So if you want, you can take epsilon of Lorentz series over SP. Right, so it's a group of local field of rank R at least 1 over the given field. So there are 3 questions. First question is, do we have vanishing? So we have this equal to 0 for every p in degrees below the rank. Now, if we are asking things below the rank, it means that maybe in the degree equal to the rank, something should happen. So the second question is, when we look at HR, we should expect that this is non-zero, at least for something. And a third question is, well, we have a space that is possibly non-zero, topological vector space that is possibly non-zero. Well, is it Hausdorff? So is this thing Hausdorff? Will you repeat? Okay, so naturally the talk is called Vanishing. So the spoiler is that we will talk about mostly about question 1. But let me say some words on questions 2 and 3 before. So on question 2, in this formulation, we already have an affirmative answer in fact. So in the non-Archimedean case, you can show that this is non-zero by looking at the simplicial cohomology of the associated proof matrix building, and you can show that this is non-zero for everything with a rather direct argument. In the real case, it's more complicated. And Boudon and Rennie showed that you have non-vanishing for large values of p. But it's more subtle because for small values of p, in fact, you may have vanishing. And there is still an interval in between where things are not really known. So we could ask a question 2 prime here, asking like what happens for these intermediate values of p in the real case. And question 3, so question 3 is known if you choose rank equal to 1. But from the very moment that you look at high ranks, not much is known for this question. I mean, you can do things on L2, for instance, because you have unitary representations, and you can show that the cohomology is Hausdorff, for instance, in the non-Archimedean case, and degree equal to the rank, and then use interpolation to pass this to LP. But it's always restricted when you pass to LP using interpolation. So it does not give you something for every p. Right. So this is all I wanted to say in concerning questions 2 and 3. Now I would like to focus on question 1. Okay, so like whenever we talk about cohomology, the first thing we do is talk about cohomology in degree 1. Because it's the one that we understand the most. And of course, this has been well studied for degree 1. So the theorem is that this question has an affirmative answer when you choose k equal to 1 for any group of rank at this group. So take this semisimple of rank at this group. Then you have that for every p, the h1 of g divided by g vanishes. And this as a term, well, we can attribute to many people. If you look at semisimple groups, real semisimple groups, this is due to Bonsu from 1999 in some unpublished notes. And later he published them around 2007. I mean, parts of it because it's huge. Then the Archimedean case was not really treated in there. So you have a paper by Bader, Frohman, Bader, and Moumont, where I think it's 2007, where they treat simple groups, both on the real case and non-Archimedean case. But the problem is that it's simple groups. So it does not treat, for instance, FL2 times FL2 is a group that we would like to include here, but it's not treated by Bader, Frohman, Bader, and Moumont, because the alternates are somewhat closer to property T. And FL2 times FL2 does not have property T. And lastly, well, if you want a full answer, there is so this is from Cornelian PCA from 2011, which essentially is some sort of Ponsus method. It's a comeback of Ponsus method in a different formulation. So Ponsus worked with the theorem of p-cohomology for manifolds, and this is why only address to real semisimple groups. But conveniente se they formulate it in continuous in terms of continuous cohomology. And in this way, they manage to well give a uniform argument for all groups, for all semisimple groups. Right.
So I had a question. Something.
Yes.
So does the vanishing of the first reference one p-cohomology for every p imply? What does it imply, like property T or like?
No. So this is just one particular representation, right?
Yeah, that's what I'm saying. Like, but even if you have it for all p, you don't get much more information about what some algebra property they do.
Like directly, I don't know. I essentially view it as a positive variance thanks to this. Like you can separate it from other groups.
Yeah, but not much more.
Not much more than that. Well, in fact, well, I am stating say a baby version of Ponce's theorem. Like what he said is something strong. In fact, he said a trichotomy between homogeneous manifolds. So he said a homogeneous manifold is either first case, its isometry group is amenable and unimodular, so it's like small. Case 2 is your homogeneous manifold has a strictly negative second curvature, and case 3 you have this polyrecurrent. So I mean, yes, in this sense you could say it's like it gives you more well, not algebraic, but more geometric information on the group. But maybe not much more than that. Like usually when you want to, I don't know, say like stronger stuff on your groups, you have conditions on the cohomology for every unitary representation or every Banach quadratic representation. Here we're again just one. So the advantage is that it's easier in something because we're working with just one representation. And I would say that well, the main motivation is this one, right? Right. Because also the other point is that well, this also allows you to treat solver groups because like every semisimple group is quasi-symmetric to a solver group by taking the Wasawa decomposition. Like in some sense, if you do things for p-cohomology or semisimple groups, well, you may hope that you can study also solver groups, which the quasi-symmetric classification of solver groups is something that remains open. So yeah, well, I don't know if very with us. Okay, I just wanted to give some ideas on the proof of this theorem. So it will appear later. So it's not even a sketch of proof, it's just an idea. And here I come back to something I said before. So a semisimple group is necessarily unimodular. So since G is unimodular, LP of G, the action on LP of G is isometric. And what I'm claiming is, well, we often like isometric representations. Now, in this talk, I claim that isometric representations are bad, and that I like non-isometric representation because of the following thing. So the idea is to pass to a co-compact non-unimodular subgroup for the R. Well, the point is that since you do this with the Wasawa decomposition, it's like a n factor inside. So G splits of KAN, you look at the AN. Because of the quasi-symmetric invariance of the p-cohomology, you can pass through this without changing the p-cohomology. And then, well, what Ponceau noticed and that community Serra exploit is the fact that when you are non-unimodular, in fact, your representation is somewhat, okay, it's not isometric anymore, but it's in some sense better because you have directions in which you contract the norm. There are certainly directions, like bad directions, where you dilate the norm, and these are bad, but you just ignore them. Like what is interesting here is that you have directions where you can have good control of the norm because it contracts. So it's like essentially they get to use contractions associated to elements G in R such that the modular function is larger than 1. Essentially, this is the main idea of congruent itself. Because elements whose modular function is bigger than 1 are the ones that maybe it's still written, yeah, because you have a negative power in here, you contract the LP norm. Right, so this is all I wanted to say on this proof, just some ideas. And now I just talked about degree 1. So let me say what is known on higher degrees. Now higher degrees, so epicohomology of semisimple groups in higher degrees has not really been studied a lot, but something that has been studied more is L2 cohomology. So let me first say things on L2 cohomology. So you have results for real simple groups, and maybe this is higher degrees for simple groups now. So for real groups, for real simple groups, you have computation due to Borel on the L2 cohomology and reduced L2 cohomology of the symmetric spaces. And in the non-Archimedean case, you also have results due to gamma angle. And that they were later improved because you have some hypotheses here on the side of the residual field. Or the residual field associated to your local field, and which were later taken out by Kasselman using totally different methods, like representation theoretic methods. But like recently, you have a paper by Greenbaum Rising in Oppenheim, where they take out these hypotheses on the residual on the size of the residual field of your non-Archimedean local field. And thus they recover like the result from Kasselman using representation theory. And like what I want to say is that Garland's proof is purely geometrical. It's really it's just local analysis on leaks of synthesis on the prophetics region. Right. So this is concerning L2 cohomology. And now concerning L2 cohomology, you have results by Godon and Dany. Which deal with, so they deal with real simple groups. Well, with some particular family that they call admissible. I will not really describe what is an admissible group for them, but the type of result that they show, so this applies for instance to SLN. SLN-R is a group to which they can apply their method. And so let me graph here. These are the values of P, and these are the degrees K. So they say one is around here, one is around here. They show something like, say, the rank of the group is around here. So for SLN, this is n-1. And say the dimension of the symmetric space is around here, which is the top dimension where you may have cohomology. They show vanishing in some small triangle, say around here. No, sorry, it's triangles here. Something like this. Where we show vanishing. And then, well, you have some point cardinal duality for the Raman cohomology that allows you to like treat some dual part. So the show vanishing is something like this. And the techniques used for this, we'll just say some more words. So they use a spectral sequence for epicohomology, plus results due to conflict. The idea is that they pass to a maximal parabolic subgroup inside your semi-simple group, and in there you can split your group using a Levy decomposition. And you're interested in the case where in the Levy decomposition you have a solvable factor. You are interested in the case where the solvable factor is quasi-isometric to the real hyperbolic space. Because in there you have conçu who make really explicit computations of the real hyperbolic space, which allow them to then use a spectral sequence that relates the epicohomology of each of these two factors to the cohomology of the symmetric product to obtain the vanishings. So, well, it's relatively hard to say. I do not want to give a more precise statement. Okay. So finally, I want to present the case of the two. So the theorem is the following. So I said that we show vanishing or homology equal to for most semisimple groups. So now I just want to list the groups that to which the method applies. So let G be a very simple group over okay. Suppose this either it can be, say, if you want to complete the example, SL4 of K, it could be G simple over your 3K of rank at least 4 and not of type. So there are some exceptions, and it's due to the type. Luckily, you show those some different diagrams. So it's not of type D4, E6, E7, E8, or F4. Well, so essentially D4 and the exceptional ones that are of rank at least 4. These are the exceptions. And third case, G non-simple of rank at least 3. So, well, in some sense, the semi-simple, non-simple groups are like the easiest ones. And the hardest ones are the simple ones. So this is why we have some exceptions in the simple case. And the result is, there exists some constant P of G such that for every P larger than P of G, you have vanishing of the epicohomology. Moreover, if K is non-Archimedean, then this constant P of G equal to 1. So essentially, it's vanishing. In the real case, it's vanishing for large values of P, and in the non-Archimedean case, it's vanishing for every P larger than 1. Just an economic way of stating like an uniform way both. So this constant P of G corresponds essentially to some conformal dimension and will appear soon in. I just want to say some parts of the group, some steps. How much time I have left?
10 minutes.
10 minutes, okay. This is okay. So I want to sketch the proof. Do you have any questions? No? Okay. So I want to sketch a proof of this result. So there are 4 steps. I mainly want to detail step 1 because it's the one that describes the setting. So step 1 is essentially like the technique from Bourdon and Ami, which is using the use of quasi-derivative invariance plus a spectral sequence. So more precisely, what we do is the following thing. So we start with G semi-simple of rank at least 3, so I will call it out the rank. And the point is that G is quasi-geometric to Q, will be a maximum parabolic. Maybe I can give an example. So if you take G equal SLN, take SLN plus 1 over whatever you want R, then Q, you will take upper block, upper triangular matrices. And say you can take like anything like this. For instance, you take one small block here and one big block here, one big block here. It's a maximum parabolic subgroup inside of SLN plus 1. Now, this group Q has what we call a Levy decomposition, where we decompose it in 3 parts, N, A, N. Where N is what we call the semi-simple Levy factor. And it's a semi-simple group, and it has rank R minus 1. Which rank of rank equal to R minus 1. And A is abelian, and it is in fact quasi-geometric to Z. And N is unipotent radical of Q. So this is an unipotent group. Maybe I can detail it in the example. What is the composition? So the N factor is essentially this big block here. The N factor is, you look at the smaller copy of SLN that lies inside of your group Q. The group A is, well, there are still some diagonal matrices in here, that do not appear here, and are the ones, these are the ones where you move this coefficient here. So this is essentially, say, lambda to the N, and here is lambda minus 1 identity, where lambda is, say, R plus star or R star. And the group N is what remains, is the coefficient here. 1 identity, and here then move these coefficients here. So it's effectively Rn. It's the example. Right. So now the point is, if you look at the group A, semi-direct AN, which appears in here. So here, you look at A semi-direct N. Well, in fact, this is always a parabolic group. So AN is hyperbolic. It's a locally compact hyperbolic group. And like the point is that for values of P larger than the conformal dimension of the boundary of this group, informally, the p-cohomology of AN is well understood. So yeah, maybe I should be more precise. I will be more precise in the next board. So I mean, I just mean that it's concentrated in the ground. So it is 0 for every degree larger than 1, and it's not 0 only degree 1. In degree equal to 1. Okay. So now the point is that thanks to this property, thanks to the fact that the cohomology is concentrated just in 1 degree, there is this huge algebraic machinery called spectral sequence that is a little bit frightening, but that thanks to this condition, it's easy to understand, and well, easy to understand. It gives you an explicit isomorphism telling you that the H2 of your group, well, of your group Q, what your group Q is corresponding to G, so you can work with G instead. Things to correspond to balance. This is isomorphic to the H1 of n with values in some space. We write LP of n with values in VP. Well, and this VP is some Banach space. It's a Banach space, and if you want to know what it is, in fact, it's the H1 of an. But you can forget that it's the H1 of an. What's important is that it's we pass from an H2 to an H1 of like LP representation, but this LP representation is Banach value. And the point, so maybe I could introduce some documentation. So if you call pi to be I'm sorry, it's the M representation on LP MVP, and if you call pi 0 the M representation on VP, so the one appearing here, I mean, like the action pi, so you take some function f in LP and VP, the formula defining the action on LP and VP is it's like a tensor. It's like a tensor representation. So you act by, say, it's like the right translation on the function, but now you will perturb it by your representation pi 0. So you will add a pi 0 on this. And now the point is that you can compute the growth of this of the operators of the operator norms of pi g. So the thing is, the operator norms of pi g are equal essentially to the operator norms of pi 0 g times the operator norms associated to the right translation. Well, with your group M is a semi-simple, it's unimodular. So this like this thing will not give you anything, and the only one that gives something is pi 0 of g. This is in LP and VP, and this is an operator norm in VP. Right? And now what I claim is that, well, this representation by 0 g, this representation by 0 is a little bit horrible. And it's, in fact, these operator norms, they grow exponentially. So this has exponential growth. And what I claim is that we do not know too much what to do with this, with a representation like this, where the operator norms grow exponentially. So what I propose instead is, well, before in the idea was, well, okay, we have a semi-simple group, we do not care, we pass to a non-unimodular group inside of it. And the idea is to use the modular function inside to break contractions. Well, here you can do kind of the same thing. So you have your group M in here. And the point is, again, use this Iwasawa decomposition, telling you that there exists a subgroup R of M, which is co-compact and non-unimodular. You can also take it solvable. And the point is that, so if you want in the example, this corresponds to just taking, you take upper triangular matrices inside of M, and this is co-compact inside of M. And now the point is, so the point is that in fact you can redo all of the work in there by changing whenever you see M, you change by R. Because in any case, it's invariant by coordinate. So you just change everything by R. And the thing is, this last equality will be different. Because in this last equality, we use the fact that the group was modular. And if you change by R, what you get is the following thing. You will get pi of G, the operator norm acting on LP. is equal to the operator of pi 0 g P times the modular function of R to the same power. And the point now is the following thing. This guy is terrible, this one grows exponentially. And we hope that if we choose the correct directions, we can maybe compensate it. And well, that is step 2. And step 2 is essentially, well, it's develop a Banach value version of the connected cell, where you change it. So the condition in the connected cell allowing you to show the vanishing was to find nice elements such that this thing is more than 1, and we change this by this thing being more than 1. So this is like the replacement. And this is like, these are the elements we want to find. And if we find them, we can show the vanishing. So, well, the next steps are basically showing that there exists, in fact. So step 3 is this guy is quite mysterious, and I cannot say anything about him. Well, step 3 is basically finding an upper bound for this guy. So it's find upper bound for this operator of pi g. And then finally, and when I mean upper bound, I mean something explicit. We want like something that can be computed in combinatorial terms. And that is the last step then. The last step is once everything has been computed and everything is all nice, we just go in and do Lie combinatorics. So that's the part where you have to well, compute everything. You compute the modular function and you compute the upper bound for pi 0 g, and you show when you see when essentially when this guy fits this one, and the groups for which it works are the fitting pairs. And that's all I wanted to say. Thank you very much.
Are there any questions for the speaker?
So yeah, so the POG is basically the smallest that thing is.
Yes.
So why is it 1 when case none?
This is just, yeah, that's just because. So
yeah,
the A semi-direct N in the real case will be a homogeneous manifold, say the real hyperbolic space.
yeah.
So it's the conformal dimension of its boundary is something like, well, if you take of dimension n plus 1, it would be n. So it's something that say it can grow. In the non-Euclidean case, A semi-direct N, in fact, it's always quasi-geometric to a tree. And the boundary of a tree is just like outer space, its conformal dimension is 0. Well, I don't know anything about LP spaces between 0 and 1. I don't say anything for P between 0 and 1.
That at least for 1.
Yeah. I just say it at P for 1 because there I am sure. But for P between 0 and 1, I have no idea.
And so, and this is for your proof that you give now is for your third case, right? For non-simple, for semi-simple, non-simple.
This what I did here, it's the second case if you want. If you take n at least 3, if you take n equals, I'm sorry, if you take n at least 4, it's the second case. It's not.
Where do the examples fail? Like in the position or?
It's no, it's just the computation.
Computation.
The computation.
It's really there.
Yeah.
Computation where you see like these examples cannot.
Or they do not work with the current estimates because the thing is this upper bound. Yeah. I am not totally sure it is optimal.
Yeah, because you don't know if those don't have a vanishing. Like you're not claiming anything about those groups.
No, I'm not claiming anything. I am not sure. I mean, it should work. And I think that the problem is just that this upper bound is maybe not optimal, or that maybe when I develop this valid version of the cognitive setup, there is some point where, there is something that maybe could be done better. Like there is some integral that I show it diverges in a totally trivial way by showing it's like the absolute value is bounded below by something that is non-zero. But of course, there are many other integrals that diverge and are not like this. So maybe something like I think it's final analysis. I think it's just like refining the analysis should give you the missing groups. And for the non-simple groups, well, the thing is like it works for all of the non-simple groups. For like it's essentially some quite trivial reason in some sense. It's just because things commute when you take two factors, things commute, and in fact this operator non-primality you can take it to be one. So like you are basically going back to the classic result of the cognitive setup.
Any other questions? All right, thanks, speaker again. So there's no formal seminar dinner, but if people are interested in dinner,